The famous biochemist Michael Smith was behind the discovery of the revolutionary oligonucleotide site-directed mutagenesis technique. Although his beginning studies were completed at the University of Manchester in America, a majority of his research was completed when he moved to Canada to study at the University of British Columbia. Here, he became a faculty member in the Department of Biochemistry, where he studied the methods for synthesizing 12 to 13 in length oligonucleotides. Prior to the discovery of this technique, many scientists would use radiation and chemicals on bacteria, which would then lead to mutations in their genomes. From the pool of resulting mutants, researchers would then select the desired mutant. This method was rather inefficient and inaccurate many times. The technique of site-directed mutagenesis was seen as much more efficient and useful in comparison to the previous methods. In Smith's lab, he used the E. coli phage Phi-X174 as a replication template. With this, he utilized oligomer nucleotides that were 12 to 13 in length as primers. These oligomers each had a mismatch at the central nucleotide in the chain. But even with this chain, the primer was still able to anneal to the template as it followed Watson-Crick base pairings. The mismatch was completed through the base pairings of guanine to thymine and adenine to cytosol, in contrast to the normal Watson-Crick base pairings. The extension of the primer was done with E. coli DNA polymerase I, also known as Clu-No fragment, as well as deoxynucleoside triphosphates. So with the help of DNA ligase, the Clu-No fragment ligated the ends of the novel strand. The final product was a DNA progeny containing both the wild type and mutant type. The discovery of oligonucleotide site-directed mutagenesis is a huge advancement from the former methods of synthesizing mutants. This technique is very applicable to many areas of life, including agriculture and in clinics as diagnosing tools. Some specific examples of it being used in the real world would be the use of it in mutations in the OASA2 gene in rice, which causes a high level of tryptophan in the mutated rice. High tryptophan levels are desired as they provide a spike in nutritional value. Michael Smith has made a huge contribution to the world of science, and without his discoveries, scientists would not be where they are today.